Greetings, chemistry students. Today I'm going to show you how to draw some more advanced Lewis structures than the ones that you learned about yesterday. So make sure you check out that first video, because today we're going to do a little bit more advanced. So let's go back to a problem that we had on yesterday's worksheet, which was the NO2 minus 1 molecule, where when you drew it, kind of looks like this. We've got 6 electrons on each of our oxygens, 5 for the nitrogens. That's 6 plus 6 plus 5, which adds up to 17. Then we also have that extra electron for the -1 charge. That gives us 18 valence electrons, or 9 pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we have a problem because the nitrogen is short a pair of electrons. It's only got 1, 2, 3 pairs, or 6 electrons, and the octet rule says you need 4 pairs or 8 electrons. So we can borrow a pair from either one of the oxygens. And if we borrow one from here, then we make a double bond on that side, or we could have done it the other way and made the double bond with the other oxygen. Now, the thing to note is that double bonds are shorter and stronger than single bonds. Double bonds are shorter and stronger than single. And as you might guess, a triple bond is even shorter and even stronger, which is why nitrogen fixing bacteria are necessary for us to live. But if we go back to this, if we have a double bond in one place and a single bond in the other, you would expect that this bond is longer than this bond. Now, scientists have some specialized techniques called spectroscopy, where they're actually able to measure the bond lengths. And when they do, they find that both bonds in this molecule are exactly the same length. And they're pretty much halfway in between the length of a single bond and a double bond, which implies that we don't actually have a double bond in one place and a single bond in another place. We've actually kind of reached the limitations of the Lewis model. But what that kind of implies is that what we have is kind of a mixture of the two. Instead of having a double bond in each place, it's more like we have a 1.5 bond in each place. Now, the way we draw this is we draw what's called a resonance structure. Where essentially we draw both possibilities and put them in the square brackets and just put a double arrow in between them. We also need to add the -1 charge because this thing was negatively charged. So this is our resonance structure. It's not that there's a double bond that's moving back and forth. That's not what's happening. It's that reality is like a composite of both of these. Now, you might ask us, well, why do we even use Lewis structures if they have these limitations? And the reason is, as you'll see in our next lesson, Lewis structures are really good at predicting the actual three-dimensional arrangement and shape of a molecule. So that's why we still hang on to these, even though it's not a perfect picture of reality in a molecule. I'll move on and show you another example. In this case, we're going to look at the sulfur trioxide molecule. This is not sulfite, 3 with a -2 charge, the polyatomic ion. We drew that in the first Lewis worksheet. This is sulfur trioxide. So we've got a sulfur, we've got 3 oxygens. We add up our electrons, 6, 6, 6, and 6. That all adds up to 24, or 12 pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have drawn all the electrons we have, but this sulfur in the middle only has 6 electrons around it instead of the 8 that it needs. So it could make a double bond with this oxygen. This oxygen can share a pair, or this oxygen can share a pair, or this oxygen can share a pair. You might guess where this is going. What we're going to end up doing is drawing all 3 possibilities. So we've got the double bond on the right-hand side. And then we could also draw the double bond on the bottom. Put some brackets around it. And draw some arrows in between. And these are the 3 resonance structures for the SO3 molecule. And you'll never have to draw more than 3 resonance structures in this class. Now, I do want to also point out to you there is a difference between SO3, sulfur trioxide, and then sulfite SO3 with a -2 charge, because you may notice from yesterday's worksheet, we didn't draw this resonance structure. We had an extra pair of electrons to put right there on top of the sulfur, which, as we'll learn soon enough, gives it a different shape. We're going to look at just one more example of this. This is a molecule I like to talk about. It's the O3 molecule, which is ozone. And we've got 3 oxygens, each with 6 electrons. Add them up, it's 18 electrons, or 9 pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And the oxygen in the middle is short a pair, so we can either make the double bond on the left, or we make the double bond on the right. We draw both possibilities. There we have it.